All right, Math 1 people, this is our first lesson in Chapter 6, Exponents and Their Properties. We're in a new unit on Khan Academy. This is Unit 13, Exponents and Radicals. And after this lesson, you should be able to complete skills 1, 2, and 3 in that unit. Our objective is that you'll be able to apply the properties of integer exponents, that's a typo, it should say integer, to generate equivalent numerical expressions. All right, so you've seen exponents before. We're just going to revisit some definitions, make sure we're all on the same page. An exponent represents how many times a number, also known as your base, is multiplied by itself. So let's say we have 4 squared, or 4 to the power of 2. In that example, 4 is the base. It's the thing that's being multiplied by itself repeatedly. And 2 is the exponent. So this is saying take 4, multiply it by itself 2 times. 4 times 4 is 16. To build on that example a little bit, what if you had 4 to the power of 5? Well, we would take that same base, 4, and multiply it by itself so that we have 5 factors of 4 multiplied together. And you can check my work, but that should be 1024. All right. So, as long as you understand that exponentiation, exponents, just means repeated multiplication, we should be able to work through these examples. So let's start off with example number 1. We have our base, which is 2/3, and our exponent is 5. So we're going to take 2/3 and multiply it by itself 5 times. So we have 2/3 times 2/3 times 2/3 times 2/3 times 2/3. And we multiply fractions straight across, so we're going to have 5 2's multiplied together. In the numerator, that's 2 to the 5th power. And we'll have 5 3's multiplied together in the denominator, that's 3 to the 5th power. And I'm okay with you leaving it there. If you did multiply it out, you should get, what is that, 32 over 243, I think. Either way. All right, let's try example 2. We have -3 raised to the power of 5. Oops. It's already there. I'm not going to rewrite it again. But we're going to take our base, -3, and multiply it by itself 5 times. And I want you to stop and ask yourself, is our final answer going to be positive or negative? And think about why. Hopefully you have an answer, an idea in your mind. Let's figure it out together. I've got -3 times -3, that's going to be 9, positive 9. And another -3 times -3 is going to be 9. I can do this because in multiplication, the order does not matter. I can group them in a different way. I can rearrange them, and then I'll still get the same answer in the end. 9 times 9 is 81. I still have to multiply by that final factor of -3, and I should get -243. So were you right? Did you think that our answer would be negative after all this? At any rate, let's move on to our last example for now. We have a base that is a variable this time. We have x times itself 5 times. That's x to the power of 5. Since we don't know what x is, that's all we can do. We just write it as an exponent. Okay, try practice problem 1, 2, and 3 on your own, and then come back and check your work. Okay, we have our base raised to the 3rd power. We should end up with 3 to the 3rd power over 4 to the 3rd power. If we have -1 to the 3rd power, we should end up with -1 as our answer. And then here we have 2 different letters, 2 different bases. And so we can write them as exponents separately. That's x to the 3rd power times y to the 3rd power. All right, before we get to negative exponents, I don't want you just memorizing rules blindly. There are a lot of properties of exponents on the next page. So go ahead and flip to page 23. We'll come back to 22. And I want you to know that even though you probably should write these all on your note card, I don't want you to just blindly memorize them. Hopefully, after we go through each property, you'll be able to see that a lot of these just fall right into your lap as long as you remember that exponents mean repeated multiplication. So let's get right into it. This first one is the multiplication rule. I've highlighted it in blue already, but notice that the base is the same. So if we have two terms with the same base and we're multiplying them together, we can add the exponents. I don't want you to just take me at my word. I want to show you why this works. So let's say you have 2 to the third times 2 to the eighth. Hopefully you would agree with me that 2 to the third power is 2 times 2 times 2. And hopefully you also recognize that 2 to the eighth power is 8 2's, 8 factors of 2, multiplied together. From there, I should be able to, I'm going to copy that and paste it. There we go. One thing we all know about multiplication is that it is associative. I can group it however I want. And because of that associative property, I can remove these parentheses. Then this is just a bunch of 2's multiplied together. And if you count up how many 2's are being multiplied together, you'll see there are 11. So this is 2 to the power of 11. And sure enough, 11 is what you get when you add 3 plus 8. So that's where this rule comes from. This isn't a proof. This is just an example to show you what's going on. All right. In the green highlighted property called power to a power rule, we have exactly that. We have a power, like 4 to the power of 2, and all of that is raised to the 6th power. So we're going to start on the outside and work our way in. We have something in parentheses raised to the 6th power, so we're going to take that something in parentheses and multiply it by itself 6 times. That's what the 6th power means. But now that thing we're repeatedly multiplying also has an exponent. So every time I see 4 squared, I can rewrite it as 4 times 4. There's another 4 squared, there's another 4 times 4. And so on and so forth. But now, I just have a bunch of 4's being multiplied together. If you count up how many 4's are being multiplied together, you should see that there are 12. 12 factors of 4 multiplied together. And that's why I can just take the exponent of 2 and multiply it by the exponent of 6 to get a new exponent of 12. All right, moving on to, we have a product to a power. Remember, the product is an answer to a multiplication problem. So if I'm multiplying 2 times 4 and I'm raising that product to a power, same idea as last time. I'm going to take the stuff in parentheses and repeatedly multiply it because that's what this exponent means. From there, parentheses I can take away because it's all multiplication. So this is 2 times 4 times 2 times 4 times 2 times 4. And in multiplication, the order also does not matter. So I can, if I want to, say that I'm going to multiply the 3 factors of 2 first, and then multiply the 3 factors of 4. And wait a minute, repeated multiplying, 2 times 2 times 2, I can write that as 2 to the third. And 4 times 4 times 4, I can write that as 4 to the third. So, again, you don't have to show your work this way every single time. You can apply this rule. This is just why this works. So anytime you see x, y all raised to the n power, you are more than welcome to write it as x to the n times y to the n. Just like that. Okay. This property here, negative exponents, that's going to be like our last rule that we go over, because the way I see it, all of these rules build up to this one and another one about zeros that we'll get to in a moment. But let's go ahead and skip down to the quotient rule that I've marked in purple. Again, I'm just quickly showing you why this rule works so that you don't have to memorize it blindly. If you have a base to a power and you're dividing it by the same base to a different power, this rule says you can write it as that base written once to the power of whatever you get when you subtract those exponents. This is why it works. So let's say I had 3 to the 8th power over 3 to the 4th power, just like this. I'm going to take this 3 to the 8th power and expand it. This is expanded form. That's 8 factors of 3 multiplied together. I'm going to expand the denominator as well. This is 4 factors of 3 multiplied together. And then hopefully you recognize that we can reduce this fraction. I've got 3 times 3 times 3 times 3 in the numerator and the denominator. Oh, in the denominator and the numerator, I should say. So this is just a big fat 1. This is 1 times the stuff that's left. So the stuff that's left is just 3 times 3 times 3 times 3, which is 3 to the 4th. But that's what our rule was saying anyways. This is 3 to the 8 minus 4, because 4 is 8 minus 4. All right. Our last rule that we're going to go over right now, that I've highlighted at least, is the quotient to a power rule. So if we have a quotient, a division problem, and we're raising that to the power of n, we are allowed to raise the numerator and denominator to the power of n separately. Here's an example of why that works. We've got 10 over 2, all raised to the power of 6. So that would be our base, 10 over 2, times itself 6 times. And again, hopefully you can see that this is 6 factors of 10 multiplied together to make our new numerator, and 6 factors of 2 multiplied together to make our new denominator. That's exactly what this property was saying. I'm not sure why you'd really use this for 10 over 2 to the 6th, but you would definitely use it if it was like 10 over x to the 6th, right? 10 over 2, you could reduce this right away and just say it's 5, and then you'd get 5 to the 6th as well. But anyway, in that last property, the quotient rule here in purple, we kind of glossed over the fact that this property implies that we could have negative exponents, right? If I switched places for 8 and 4, and I had 3 to the 4th power over 3 to the 8th power, I would get a negative number, wouldn't I? According to our quotient rule, I should be able to subtract these. 4 minus 8, that's negative 4, right? But our quotient rule says this is 3 to the 4th over 3 to the 8th, right? And again, that's 3 times 3 times 3 times 3 over 8 factors of 3 multiplied together. And again, this is just a big fat 1. But then we'd be left with 1 over 3 to the 4th. So, you may not have seen negative numbers in your exponent before, but this is why it works. It comes from our quotient rule. If you have a base raised to a negative power, you are allowed to change that negative power to a positive power as long as you flip the base or use the reciprocal of the base. So in this case, our base was 3, and the reciprocal of 3 is 1/3. So 3 to the power of negative 4 is the same as the reciprocal of 3 to the power of 4. That's what this rule says right here. Okay, so I threw a lot of properties at you. Bear with me, I have one more for you, and it's actually back on page 22. On the left margin of your notes, you should have a box that says anything to the power of 0 is always 1. And I'll be honest, I need you to put a caveat on that. We have some fine print. This anything really means anything except 0, right? You're not allowed to take 0 to the power of 0 because it ended up being dividing by 0. I'll show you why. And again, this comes from our quotient rule. So here's our example. Switch over to pink. So hopefully you agree with me that 1 is 8 divided by 8, right? But what I'm going to do is take those 8s and write them using exponents. I could say 1 is 2 to the third power over 2 to the third power. You can double check. 2 times 2 is 4 times a third 2 would be 8, right? But from there, wouldn't that be saying that 1 is 2 to the power of 3 minus 3? According to our quotient rule, right? We can subtract our exponents. But what is 3 minus 3? It's 0, right? So 2 to the 0 power is 1. The thing about this is that 2, the base, is not unique. I can write anything I want to the 0 power, and using that quotient rule, I can reason that it's got to equal 1, right? So I can say, I don't know, 5 to the 0 power. Well, wouldn't that be 5 to the first power over 5 to the first power? That's 5 to the 1 minus 1. But anything divided by itself is 1, right? The only time this doesn't make sense is if I use 0. If I use 0 as my base and raised it to the 0 power, I could say, well, oh, that's 0 to the first power over 0 to the first power, because 1 minus 1 would give me 0. But the problem is, now my denominator is 0. And remember, we can't divide by 0, right? So for our 0 power rule, anything really means anything except 0 to the power of 0 is always going to be 1. And it's not defined. We can say, I don't know, draw a big sad face and say undefined. 0 to the 0 power, just kind of, we don't know. It's not defined. All right, so now that you've seen all the properties, we can go ahead and fill in this blank here. Negative exponents mean you do the reciprocal of the base. Let's try example number 4 together. We have 4 as our base raised to a negative exponent. So I can make that exponent positive as long as I replace the base with its reciprocal. So the reciprocal of 4 is a fourth. This means it's 1/4 times 1/4. So our answer should be 1 over 16. Example 5. Again, we have a negative exponent, so I'm going to change that exponent to be positive, and I'm going to flip the base. So the reciprocal of negative 3 is negative 1/3. So I'm going to have negative 1/3 times negative 1/3 times negative 1/3 times negative 1/3 times negative 1/3. And I should end up with 1/9 times 1/9 times negative 1/3, which should end up being negative 1 over 243. Last example, we have 2/3 to the negative 5th power. The reciprocal of 2/3 is 3/2. And now I can say that's a positive 5 in our exponent. And according to our exponent rule, our quotient rule rather, 3 to the halves to the 5th power, that's 3 to the 5th power over 2 to the 5th power. You can leave it like that, or if you'd like, you can multiply it out and say it's 243 over 32. Try practice problems 4, 5, and 6, and then come back and check your work. Okay, so practice problem 4. We're going to flip the base and make the exponent positive. So that's 4/3 times 4/3 times 4/3, or 4 cubed over 3 cubed. Practice problem number 5. We flip the base, make the exponent positive. So we have negative 1/5 times itself 3 times, which should end up being negative 1 over 125. And our last practice problem is number 6. We switch that to be 1/2 to the 5th power, which is 1 over 2 to the 5th power, or 1 over 32. Awesome. And then again, these will come more naturally to you as you keep practicing them. For now, write them on a note card so you can refer back to them. Keep your notes close to you as you do these problems. All right, last set. Let's do the examples together and the practice problems on your own. We have 11 squared over 11 to the 4th. According to our quotient rule, that's going to be our base to the power of 2 minus 4. And I know what 2 minus 4 is. It's negative 2. And my negative exponent rule says that I can write the reciprocal of the base. The reciprocal of 11 is 1/11. And then the exponent becomes positive. So that's 1 over 11 times 1 over 11, which is 1 over 11 squared, or 1 over 121. For example 2, I see the same base show up twice. So I'm going to use my multiplication rule. I'll leave the denominator alone for now, since the multiplication rule only works when I'm talking about the same base. So I'm going to rewrite that as 120, and I'm going to add the exponents. So negative 2 plus 2 is what we would have. But negative 2 plus 2 is 0. And any non-zero number to the 0 power is just 1. So I've got 1 over 7 to the negative 3rd power. I am allowed to flip the base. So I can flip 1/7 so that it's just 7 if I make the exponent positive. So that's 7 to the 3rd power. And I'm just going to leave it like that. But you could also write out 7 times 7 is 49. 49 times 7, I think it's 343, right? Check my math on that. And then our last example, we have some variables, but we can still apply these exponent properties in the table we have above. So I've got x squared times y over x times y to the negative 1. And because we're just multiplying, we can actually write this as two different fractions. This is x squared over x times y over y to the negative 1. Please keep in mind that if there's no exponent written, then it's really a 1. You don't have to write it, but there's an invisible 1 there if there's no exponent at all. But from there, we can use our quotient rule. So for this first quotient, we can say that that's x to the 2 minus 1 power. For the second quotient, we can say that's y to the 1 minus negative 1 power. We're subtracting the exponents, right? And 2 minus 1 is 1. I don't even have to write anything, that's just x. And y, 1 minus negative 1 is 1 plus 1, which is 2. So our final answer should be xy squared. All right, try practice problems 1, 2, and 3 on your own. Then come back and check your work. Okay, practice problem number 1 should look like that. You can reduce this fraction at any point in this. I chose to reduce it right away, but if you had 6s and 3s going down, that's fine too, as long as eventually you reduce. Practice problem number 2, we add our exponents. We should get 5 to the 5th power. And practice problem number 3, we multiply. We should get 3 to the 16th power. As always, ask a question at the end of the video, and I'll see you all in the next lesson.